Okay. All right. Hey, can you guys see me? Well, hopefully you should be able to see me. Okay. Am I audible? Okay. I'm guessing you guys can hear me, and I'm guessing everything's working fine. So let me just get started. So today I thought I'd actually pick a library called rust-libp2p. It's basically a peer-to-peer library that allows us to write peer-to-peer applications. But the key thing is that this is written in Rust, and it's a modular, stack as such. So let me get started with this, and I'm going to be switching between the chat and VS Code and stuff. So you guys can go ahead and just drop your questions in there, and I'll keep switching back and checking in. All right. I still have to figure this whole thing out, but so I'll just get started with this. Okay. So here's what we have, and I hope you guys can see the font. I think it's big enough, I'm guessing. Yeah. Is the font good? Yeah. I'll just assume it's good. So, all right. So we're here. Let me see this. So this is the first time, or rather, I just started looking at this library, and I was wondering how can you get started with this? Because we've been exploring options when it comes to building out, firmware distribution platforms that we're looking at. So the idea was, let's just take a look at rust-libp2p, or rather the libp2p implementation in Rust, and see how it works. I've been able to gather a couple of things. One is that this makes use of a lot of async. So it's that kind of makes sense because this is a networking library. So, and that's where async Rust actually shines or is required. So that makes sense. So before we get into the details of things, let's actually understand, before we get into the implementation, let's actually understand what libp2p is. So I thought I'd actually go to some of the documentation over here and see what that looks like. So firstly, how do we get, actually, you know what? Let's go to the main page. So libp2p is been around for a while now. So as you can see, it's a modular networking stack. So it's basically, the way I'm looking at this is a bunch of different protocols and a bunch of different things that have been out there for a while. They've been packaged and packaged into modules, and sort of stuffed into this networking stack. But the key point is that unlike your traditional networking stack, which is say TCP/IP, this one's peer-to-peer. Think BitTorrent and stuff like that, right? Makes sense, right? Okay, so if I was just looking at what's available over here, there's actually good. There's a lot of content available for this, I guess. I presume this has been around for a while now, so I believe there's quite a few protocols in terms of, let's say, transport protocols that it supports. It supports stream muxing, we'll talk about that, which is basically on the same connection, you'd like different types of data streams to be sent across that single connection. And things like, of course, it being peer-to-peer, etc. But I was looking at a couple of things. One is, let's look at the implementations available. So apparently there are a bunch of implementations available, which is, you've got all of these. You've got it in Go, in Rust, in JavaScript, NIM, C++, Swift, etc. And I was looking at what sort of do we have, like, is Rust the best implementation, or rather the more full-featured implementation or not? And I see that actually Go was the first reference implementation for libp2p, and then came Rust. I don't think Rust came after that, but I believe Go is the first libp2p implementation, and it supports all of these different transports. And I believe it also supports different kinds of NAT traversals. NAT traversal is basically, you have a local network and you're sitting in the local network, but you actually have to communicate with someone over the public internet. How do you do that traversal between these local private networks and the public network? That is one big problem, and I think that's also been addressed over here. And then you also have secure communication. So by default, everything in libp2p is encrypted and authenticated. I believe it is authenticated. Yes, I'm not sure, but let's double check that. So the two communication protocols, or secure communication protocols, that it supports currently are Noise and TLS. Noise is actually a framework. If we have time, we'll sort of jump into it. And then we also have Discovery, which is, this is the key part. This is where libp2p sets itself apart, saying it's not like a traditional networking stack. When we talk about peer-to-peer communication, we are talking about, the biggest thing that we're talking about is there's no central authority or central server that's coordinating or providing resources to you. You have peers that are basically talking to each other and fetching content, or rather files, etc. And how do we discover them? How does one peer discover, how does one node, a node in libp2p is basically one, you can just think of it as one machine that's part of the network, part of the peer-to-peer network. And if it would like to sort of get some resource, it needs to know, it needs to be able to do that. And in order to do that, it needs to know, okay, who are my peers? Who am I directly connected to right now? And then check with them to see whether those peers have that content. If they don't, can you tell me who has it? Can you give me an indication where I can go find this? Where should I go to get this? So that kind of, all those pieces, all those protocols that are revolving around discovery and peer routing and pub/sub, etc., in the context of a distributed network. All of these things are what will be new when we talk about libp2p. So there's a ton of things, and I believe the site does a good job of talking about what is the feature, what features are implemented for which implementations, and how stable or mature they are. Yeah, so I'm not going to go into this because we'll take a look at the implementations per se, but just to give us an idea what's available, what we can look at, etc. Okay. Yep. I hope that makes sense. Right? Okay, let me just quickly check the chat. Any questions? I don't see any questions, so all right, let's go. Okay. Then, yeah, we just talked about all of these things. So let's just jump back into VS Code and look at, so I've already done, I've just saved some time. I've already cloned the repo. I've started looking at it, and well, it's pretty well documented. At least I would say that, you know exactly where to go find API level documentation or even user level documentation. I think that's good. So actually, let's get quickly started and look at the first example. So let's actually look at the rendered output. Yeah, I hope this is good enough. Yeah, is this good enough? Can you see the screen? Okay. All right. So if you see this, there's main documentation. Obviously, this is our, we want to open this. This is our API level documentation. This is exactly what we want, which is effectively allows us to use this particular crate pretty well. So I've looked around and I see that this is well documented. We'll come to this, but before I go there, let's look around and see what else we can find over here. So you got the main documentation. We can do, you can file security bugs and stuff like that. You have questions, you can ask them in the discussions page. I believe they also have a matrix channel. Do they? Okay. Yes, not. Fine. All right. So here is the main structure. They have core, which contains the core implementation, I presume. It implements libp2p core with its transport and stream muxer API. Okay. And then they've, which is very nice, separate out all the transports into their own little crate. TCP and all of that stuff, whatever is supported by libp2p, all the transports, you can just chuck them into one separate section. Then the muxers, as I said, this is basically when we talk about muxing, we're talking about stream multiplexing, in the sense that I have a TCP stream, I have a UDP stream, I have an application, a different kind of application, that's a different kind of data that's probably moving through my channel, my connection. I could move it. So, I use the word TCP and UDP stream. That's this transport actually. You can think of different kinds of application data. So if I want to move, I don't know, chat data, if I want to move, or ping data, if I want to move any of these things, if I want to move them over the same connection that's already been established, because establishing a connection is expensive. You actually have to go through the whole negotiation, handshake, whatever it is, depending on what kind of connection you're establishing. So reusing an existing connection is very useful, and makes the system actually very performant and efficient. And it's what stream multiplexing allows us to do, and they've implemented that over here as well. For example, some transports like Quick, which is sort of Google's evolution of TCP, it supports stream muxing by default in the implementation itself. Now, this one's probably going to say that, okay, we will look at all the different transports out there, and we'll figure out how do we add stream muxing on top of all of them, right? I presume that's what they're going to be doing, because they're saying typically TCP connections as well. And then there's a swarm. Swarm is an implementation where basically what I understood over here was the swarm is nothing but it's like the manager. It's like the libp2p manager. You can think of it that way on the node, on your particular, let's say you're running a peer-to-peer node. The swarm that's part of that peer-to-peer node is going to do a lot of management work for you. Okay. We'll look at this. I think I've got a few pieces figured out, but we'll look at it. And then we've got protocols. Now, these protocols are what sort of makes libp2p very different. They've come up with multiple protocols to be able to do this peer-to-peer networking. You can think of things like file sharing, or file sharing is not just a protocol, but let's just say we walk in here, we sort of look at this. So all of these are actually protocols that work with or are supported by libp2p. Things like auto NAT traversal and flood sub, gossip sub. I don't know what DC UTR is. Let's see what that is. Direct connection upgrade through relay. Okay, I'm presuming this has something to do with NAT traversal, but let's look at it later. But anyway, yeah, so all of these different kinds of protocols have been developed and are supported by libp2p. And I believe some of them actually only make sense in the peer-to-peer environment. Things like flood sub or gossip sub, etc. CAD is Kademlia. There's a bunch of papers written on this, etc. It's very interesting. I just started looking at it. I think we'll have more time to look at it, but at least let's understand the basic layout of this particular implementation and sort of how it works. We'll take a simple example, and if time permits, we'll sort of dive a little deeper in. And there's a lot of async stuff as well. So I don't know if I'd be able to write code and actually make it work, but let's see. At least we have examples, so we can run those examples and see how they work and sort of infer what's going on. Okay, so far so good. Any questions on this? Okay, all right, that makes sense, I believe. So let's move on. Okay, so let me just close all of this stuff. And since we've been through all of this, let's just jump directly into an example. So before we actually jump into the examples, let's take a look at this repo. We've looked at the README, so that's what we've been able to gather, that there's good documentation available. There is there's the layout of this particular repo is sort of given to us. Now the first thing that I'd like to do is actually take a look at all of the different dependencies and extras that we need to be aware of. Of course, there are features and stuff. There's a whole bunch of features because it's a massive library. It's obvious. It's a modular networking stack with so many different transports and protocols and all of that. So that makes sense. That's not a big surprise there. But yeah, let's look at the dependencies. Okay, so there are a ton of dependencies. Most of them are just basically sort of pointing. I'm presuming all of these are libp2p versions of the protocols, right? Yeah, the path. Sorry, I was thinking something else. Okay, yes. So everything is basically pointing to, one of the, at least the main workspace has all of these dependencies, which actually are pointing to crates within the repo itself. So that's fine. So let's actually go and take a look at core, because, they called it core, which means all the basics, foundational stuff is in there. So let's take a look at that. Okay. All right, so what do we have here? We have got core traits and structs for libp2p, which basically means all the different types and traits that are required for libp2p is present here. Oh, by the way, the author is Parity Technologies. I think I know them from their crypto, the crypto space. Don't know too much, but I think I've heard of that name somewhere. But anyway, so there's ASN1DER. So ASN1DER is basically nothing but, your X509 certificates, the format in which they are encoded. Let's actually, it's a good thing to actually think about this, because rarely do you get to actually revisit those concepts. Let's say DER, certificate format. So if I click this, I could actually run a curl, but I just wanted to, let's see, where is that? Yeah, so basically this is, these certificates that you see over here, which is these certificates. And these certificates have what you call, where are they? Oh, wait. Yeah. So this particular certificate, you can either encode this in a binary format, or you can have this in a more textual format. The textual format is basically what we have here, which is the PEM format, which is what is called privacy enhanced mail. Oh, good. They have this button here. I'll just click this. This is what it looks like when you take the same certificate and have it in this encoded format. You have, that's the PEM format. It looks like this. But if you want to look at DER, it looks like this. All right. It's just binary versus textual. And I believe that crate is important because we're dealing with quite a few crypto concepts over here, from noise and TLS. So that makes sense. BS58 is, what is BS58? BS58. Oh, base encoding. All right, it's basically another encoding. Lots of encoding stuff. I guess there's a lot of formatting stuff that's required. This is nothing but a crypto, elliptic curve cryptography, or this is basically the Edwards curve. Fine. Either is also used. Either is nothing but, it's like your result type or your option type, except that you have a left and a right. This is directly from functional programming. We can talk about it, but that's good. Okay, we're just not going to go through every single one of them, but we'll just look at this. FNV, fine, we'll look at it. Futures. So as I said, this entire repo makes heavy use of async. So obviously there's the futures crate and all of the, all of the stuff that's inside a futures timer, instant. Multi-address and multi-hash are two extra concepts that we would probably have to understand. And I think I found a very nice place, or some website, some applications that are available online to sort of explain that concept very, very easily. We'll go through that. Then P256, Prost is buffer, the protocol buffers. All right, yeah. There's a lot of serialization, deserialization, encoding, decoding stuff. Async, async program, basically async stuff that you need to write, async code that you need to write. And then there's the very specific things like multi-address and multi-hash, which are the specific pieces that you'd require for in a library like libp2p. So let's look at that, because the rest of these things are all just supporting, crates, I presume. So let's look at multi-address ones. Okay. Multi-address format. Lib2p, maybe. Okay, that should work. Let's look at this. Yeah. Okay. Okay, a multi-address is a convention for encoding multiple layers of information into a single future-proof path structure. Okay, I get it. So what is happening is, I just scrolled down, I saw this. So typically when we talk about connecting or identifying, identifying a machine on the internet and trying to connect to it and then send some data to it, and then the machine that we're connecting to gets that data and processes it and sends a response. The way you'd want to actually talk about it in the traditional TCP/IP setup is you basically just say, okay, this is the IP address and this is the port number. I want to connect to this machine. That's what we say. In the multi-address piece, what's happening is you're basically saying that I want to actually connect to the machine that's speaks IPv4, whose address is this, and I want to use the transport 4242, and then I'd like to use p2p. That is the peer-to-peer lib2p, lib2p, and I would like to use this specific protocol on top of it, which is relay, circuit, whatever that is, right? So that's basically the multi-address format. And this is one way of looking at things. I presume this is very specific to the lib2p peer-to-peer connections, and that's kind of what I think you get over here as well. Things get more interesting as we compose further. For example, the multi-address uniquely identifies my local IPFS node exactly using lib2p's registered protocol ID, which is p2p, and the multi-hash of my node's public key. Okay, I hope that makes sense. I think that sort of makes sense, right? But anyway, I actually found some interesting tools available. Let me see if I can find them. Okay, not you. I think I remember this. Right. I don't remember. Where did that? Okay. By the way, this is IPFS. IPFS is the original project that talked about building a distributed file system using basically a distributed network. And lib2p was actually one of the core sort of libraries that was used to build out IPFS. But they saw that lib2p itself is a project in its own, and they sort of rolled it out. And now it's a project by itself. Of course, it's one of the dependencies for IPFS, but IPFS is the main thing that is being built out as a file system that's available in a distributed, using a distributed network to build a file system, right? The only thing I'm trying to see is there's this very visual way of showing. Okay, I think this is it. Let's see. You know what? Let's just go to the thing. All right, I think this is pretty straightforward, right? If you'd like to generate a multi-address, you basically provide the address and then you say parse. It's going to go ahead and build the address for you. And these are the different kinds of addresses that, like, these are two examples of multi-addresses. So this one over here is saying that this is a multi-address where we're connecting over a peer may be connecting over IPv4 using the local host as the IP address, and the transport and port number is 1234. Second one says IPv4 using this particular IP address over UDP, port number this, and uses quick v1 on top of that, right? Makes sense. Okay, let me just check the chat. Any questions on this? I guess not. Okay, let's just go forward. So that's multi-address. Yeah, I'm pretty sure we'll have more questions on that later, but let's just keep moving. All right, and then multi-hash. This, I believe I have a bit of an idea because I was actually looking it up. So now I just need to find one. Let's see if the tutorial has. Oh, come on, man. Just give me an example, like a full example. I will go ahead and decode it. Great. Just when you want something, you'll never be able to find it. Yeah, got it. Let's go back here. All right, we got it. So multi-hashes is nothing but, let's say you have some content, and I'll talk about why we're talking about multi-hashes, because multi-hashes specifically it makes a lot of sense when we talk about IPFS, because in a distributed network, how do you actually uniquely identify content when there's no central authority to provide you with a resource? So you can't just say, I'm going to go to this place and I will ask for this resource and I will be provided an authentic resource, because there's no such thing as a central entity with authority in the IPFS or network, or what's called a peer-to-peer distributed network. What happens is you take content and you actually sort of hash the content to produce a unique signature or a unique fingerprint for that content, which is called a hash, which is nothing but this little thing that you see here. In this case, if you actually look at it, it says we've taken whatever piece of content this thing refers to. It's been hashed by SHA-2, 256-bit hash, which is nothing but 32 bytes. Wait, I don't care. Basically, it's been hashed by SHA-2, and the idea is that it's also encoded in the protocol buffers format, and there's a version number attached to it. And there's also, finally, after all that, then you do what is called some additional ASCII encoding with base 58. It's basically a representation, a way to represent that unique fingerprint in different contexts. For example, let's say if I don't want to use SHA-2 hashes, I want to use something else, a different hashing algorithm, I can still go ahead and use this method because I am clearly calling out what is the hashing algorithm I'm using, what is the length of it, what is the type of it, etc. That's what this multi-hash is. And so I just pulled some value from the internet over there, and I went ahead and entered it over here. As far as we're concerned, with the immediate question that we have, multi-base, multi-codec, and all of that is not important. Multi-hash is what is important, right? So if you look at multi-hash, when this thing was decoded, when this entire string was decoded, we got a multi-hash value that said code hex 12, which basically is SHA-2, 256, bits, basically 256. And the digest value was this, which if you were to convert to hex, that is decode from base 58 to hex, you would get this, right? That's basically a multi-hash, right? Okay. All right. And then there's multi-stream select. Multi-stream select is nothing but to do with stream multiplexing. I sort of have an idea. I looked at it. We'll talk about it. So basically, this is when we talk about core libp2p implementations, this is kind of what it's dependent on. So we get an idea of what we can expect when we start looking at this implementation. Now, should we look at the core implementation, or should we just go look at an example? Because that way, which one? Let me ask the chat. Look at core impl or, an example. Okay, Josh wants his example. Cool. All right, let's just look at the example. Because yeah, you're right. You'll have to sit through the whole core piece and figure it out. Maybe an example would be an easier way to sort of get through. Okay, let's look at what's going on over here. How about we take, nothing complicated. We'll just take ping. And let's dive through it. So, always read the documentation so that you don't end up pulling your hair. And you know that it has documentation. So if we were to ping, what's going to happen here? So see source tutorial.rs for a step-by-step guide building the example below. Oh, there is a step-by-step guide. Where is that? Source tutorials. Interesting. Let's just look at this on the website. Right, so all of these are the implementations. We are looking at rust-libp2p, and we got source, tutorials, ping. Oh, this doesn't look like. Okay. This is like a doc. Wait, I thought this was going to be a document. What happened? Okay, screw this. Let's just go read it. Let's just go walk through this ourselves. Anyway, okay, so basically if you want to run this example, you just call this, and we should get this, and we should also be able to test it out. So let's just run that, see what happens. I've got two of them over here. I was just doing some testing. So So I probably need to go into, where's that? Examples. Yep. And where I'm going to ping. Wait. Oh, wait, I don't need to do that. Sorry. Okay, let's just do this. We'll let this build, and then we move in here, and then obviously we'll need to wait because presume we'll need to get this, the multi-address. See, this is why you need the multi-address. And hopefully I'll just wait for this. All right. I'll just, so it's listening on these two particular multi-addresses. What happened? Oh, sorry. All right. That makes sense, right? You get a ping and a pong event. I don't know if they'll keep doing that. Doesn't look like they'll keep doing that. But yeah, they will keep doing that. So let's just actually just, let me just zoom this out and see what's happening here. So we, I believe we've got a peer-to-peer ping application that's been set up. What's happening here is, first things first, a peer ID is generated. We'll talk about that. And then we start listening on those two particular multi-addresses. And so this peer ID belongs to this terminal, let's just say, and this peer ID belongs to this terminal. So basically each of them, I think it's sort of mentioned over here. The two nodes establish a connection, negotiate the ping protocol, and begin pinging each other periodically, I presume. Yeah, periodically. Every couple of seconds, you seem to be getting a ping. The idea is, this is not your traditional ping. That is your ICMP ping from TCP IP. This is like a TCP ping. That is, you establish a TCP connection, and then you have both of these peer-to-peer nodes that are pinging themselves. So of course, both of them are running on my local machine, but the idea is you could do this, in a peer-to-peer fashion over the internet. All right, so I'm going to go ahead and stop this. I think this makes sense. So let's just stop this. Just to confirm, this is the first few, that's the first few characters of the peer ID for this machine. Let's just check if this is the same. Yep, this is it. So this is the peer ID of this particular node on this running in this terminal. Okay, and the peer ID for the other one, sorry, I think I'm looking at the wrong ones. THK79K, so I presume this is, yeah, THK79K is pinging the other guy. And then I presume GQES5. Yep, that's this one. Makes sense. All right, so I think this is a fairly simple example. We just built, or rather, we just compiled and built a peer-to-peer ping, application, right? That makes sense. And I don't think there's any questions on this, so I'll just move forward. Let's look at what's happening. So we saw that the first thing that happened was we printed out the local peer ID. Now, one of the most important things about peer-to-peer networking is you need a way to uniquely identify your libp2p node. That's a libp2p node from the other on the internet. And the way they do that is through our traditional key pairs, which is you basically generate a pair of keys. Here you were using the Edwards curve, again, ED25519. When we generate that, we go ahead and pull the public portion out of it. I believe, yeah, get the public key out of this key pair. And then that's our, we basically, I presume this is going to go ahead and take a hash of that public key. And that's what our peer ID is. It'd be interesting to see right, it's a multi-hash. It's peer ID is nothing but something that wraps a multi-hash type. So fine, that makes sense. So that's what I meant. So we actually go ahead and get the public key and run it through a multi-hash, and then we say that is our local peer ID. Right? That makes sense. Then the very next step is, once you have a peer ID, you'd like to go ahead and say, okay, great. Now I also need to talk about my transport. What transport am I going to use? I'm going to use TCP, Quick, a whole bunch of other things that I have, etc. UDP, etc. So I believe I was looking at this earlier, and let me just make this a little smaller. I believe, well, quick question. I don't think there's anything's being cut off, right, on the screen? Yeah. Because I realized some time ago things were cutting off. Should I just remove this? Then that should help, right? Does this help? Okay, I'm going to assume that now it's not okay. All right, yes. Okay, Lavanya said yes, fine. All right, so we have a transport. We just built a transport over here. And by the way, we're quickly running through all of this. We can actually dive into the types and the entire async stuff. I was reading some of the documentation. I think what they're doing is they got an interesting idea. I'd actually like to see how it's actually working out for them. Remember we talked about asynchronous Rust, and when we talked about that, we talked about futures, and then we talked about how an async block is converted into a state machine. When the compiler actually sort of looks at an async block, it converts that into a state machine with different states, all the different await points of states in there, and then we sort of move forward. Like that is, then yeah, basically we generate that state machine, and then we start polling that state machine to keep moving forward, right? We sort of discussed that in one of our workshop sessions. Here, something very similar, not something very similar, it is essentially the same thing, but they've taken it to one level, one more level of complexity. Instead of a single state machine kind of a scenario, they're actually building hierarchical state machines, in the sense that I will show you what I was reading. So one state machine might have child state machines. The parent state machine might keep driving the child, state machines to completion. So we look at that. That's sort of the development philosophy or design that they've adopted. Apparently there are benefits to that, which unless we look at it, we wouldn't know exactly what they are. We just have to take their word for it. Yeah. So anyway, in this case, we got a local peer ID, and then we say, okay, give me a transport. This is this transport layer. Okay, why there's no documentation? What? Why? Fine. Anyway, some reason the documentation is not being pulled up, but this is not a production transport. This is something that they've provided just for examples and stuff. And then we have our lo and behold, our await point, right? Because main is actually an async block, but if you see on top, this is using async std. It's not using Tokyo, it's using async standard, right? That makes sense. Then we have, once you do that, once you have your transport and basically you have a peer ID, you've got yourself a peer ID, you said, I'm going to use this transport. The development transport, I believe it is a TCP transport. We'll have to check that. But anyway, you pass the local key in over here. So that's fine. By the way, this step is not required. That means if you're writing actual code, you wouldn't actually do this unless you wanted to print the peer ID. Okay. It's automatically, like for example, in this transport, when you pass the local key, it does the same thing. It extracts the peer ID in the same manner that we just saw. Anyway, then we have this transport. We will look at this. This is allocated on the heap. That's why the type boxed is being used. So I think this is something that people often use, where you want to talk about something being allocated on the heap, just say it's boxed. Boxed is not a standard library type. It's actually a type from, probably, let's actually look at it. Yeah, it's a type from, the core library. Oh, okay. When did that happen? All right. Maybe I missed something. Anyway, so this type is from the core library. It basically says, oh wait, what am I saying? I thought this was from the Rust core library. No, this is actually from the rust-libp2p core library, or core crate. They have the transport section in there, and they've got their own box type. Okay. That makes sense. So it's basically a transport that's being allocated. Where do you want to actually allocate this? On the heap. Well, I put it over there. Okay. Then we'll come to the stream muxer box is we'll just come to that. Then we go ahead and create or instantiate a swarm. As I told you, the swarm is nothing but your actual manager. You can think of it as the manager, but it's the thing that connects everything up. It's like, you can think, at least right now, I'm thinking that this is like in the hierarchical set of state machines that this particular library talks about. I believe swarm is like the parent state machine, possibly. Yeah. And we're going to go ahead and create that swarm using an async standard executor. It's like, rather than Tokyo's executor, we're using async standards executor, which is much simpler and much cleaner. I actually think that is the case, because Tokyo does get quite complex. But anyway, then we pass in our transport, we pass in our, this behavior thing is very interesting. We'll come to it. And then we've got the local peer ID that we just created. So we pass these three pieces in, we get our swarm. So let's come to the behavior part. What is the behavior? If you actually look at it, the behavior is, what does your node actually do? What is the behavior of your node? In other words, we just created a pinging node. That is the behavior of this node. It can behave like a pinging node. Okay, a ping pong node. Then you can have other kinds of nodes, which all the protocols, basically all of those are behaviors. Right? So that's an example when you want to talk about what behaviors are. So there's a very close relationship apparently between the transport and the behavior. In libp2p, apparently according to the documentation, any type that implements the transport trait is a transport. Any type that implements the behavior trait is, as behavior. All right, that's just, for us to sort of visualize this at least. And then once you create the swarm, you listen. You call its listen on. It's like, this is nothing but I think the simplest way you can think about this is you can just say that if you were using traditional socket programming, you say TCP create socket, or rather you create a socket and then you say TCP listen, and then you pass, your socket address or something like that in there. Very similar. So this is the method, this is the multi-address that's used if you want to actually say listen on all possible interfaces, because you saw over here, you saw that we were listening on, where is that? Yeah, you saw over here that we were listening on these two interfaces, right? And that's pretty much what we're talking about. Listen on all interfaces and pick a random port, a random OS assigned port. That's why the port numbers were changing over here. That makes sense. Yeah, that does make sense. So this is 58146. This is 58147. All right, and then once that is done, this is the peer that was dialed. For example, on the left, in the left example, let me just make this bigger. You see this? We are not dialing a peer over here. We're just creating a peer. We're just generating a peer ID, initializing the entire node, and saying we're listening on 58146, which is the port number. But here on the second node, because we have passed in an argument, which is, we're saying go ahead and ping this particular node, because we've passed that in, now we get to go ahead and actually dial, that particular node, right? So that's the little thing. That's why we're doing an if let sum, which is if you have, a second command line argument, go ahead and do the dialing as well. That's only for this example case, right? And then once that is done, we talked about the example said is both of them are going to be pinging each other periodically. That's kind of what's happening here. It says, okay, now that everything is set up, once you actually get a connection, you guys can start pinging each other periodically. So, yeah, where is that? TT. Okay. So we got listening on address, which is basically what we just saw, which is this part, listening on. And then swarm event, behavior event, print event, which is this part, which is what we're printing over here, the events. I'm just trying to figure out where the pinging is happening, periodic pinging. Not here. Let's just dive in here. That's interesting. I was actually going to jump into the swarm and the events and stuff, but before we do that, that's interesting. Where are we actually saying ping? Does that happen automatically? Okay. The default behavior. So There's something that I'm probably missing. Our network behavior for illustrative purposes, this includes keep alive behavior, so a continuous sequence of pings can be observed. Okay. So there's something happening over here that we need to sort of dive into to look at it. So this behavior that's being passed in is right here. And we are saying use the ping behavior. So if I was to what? Why won't you? Okay, where is ping, man? Yeah, right here, no? What am I doing? Lib p2p identity ping. Let's just go over there. Lib p2p. We'll presume it's here. Oh yeah, that's pretty much what they're saying over here. So if you see this, they are saying that a network behavior that responds to, this is when we actually jump into the ping particular ping module over here, you see that they've built a behavior by default that responds to inbound pings. So if you sort of highlight this, it responds to inbound pings and periodically sends outbound pings on every established connection. Okay, so that's sort of by default in the example. We're wondering why is it not being done. Anyway, questions so far on this? Okay, this kind of makes sense, right? At least given all of this traditional networking stuff that we've done, peer-to-peer networking doesn't seem that different yet, because we haven't touched the real peer-to-peer protocols as such and understood them from a much more deep in-depth perspective. Okay, so this is a very basic example of what lib p2p actually does. Now what should we do? I think we're sort of on time, but you want to discuss something else as well? This is just to sort of get us up and ready, because we will anyway discuss this a lot more. Yeah, so any questions on or rather any ideas on what you'd want to go for next? Because I was going to cover some of the types, because these types are very they're quite interesting. We'll take a look at that, but I just wanted to check with you guys if you want to cover something very specific. Okay, cool. I think we can do the IPFS thing. Yeah, cool. Yeah, we can do the IPFS on the next stream. Right? That's a very good idea actually, because it would make a lot of sense to sort of build on top of what we've just sort of looked at today and what we will look at in going forward as well. And basically, because IPFS predominantly, I think from our perspective, how do we build a firmware distribution platform is a very, very interesting topic for us. And the entire IPFS network, which is built on files, or rather being able to share files in a distributed network, is the key point. And I think it's a very good fit. But one of the important thing over there is I don't know if any firmware distribution platform ever needs things like immutability, etc., because we don't know whether the firmware wants to be there. On something like the IPFS network, one important thing that we have to take into consideration is the entire file system is immutable. I will talk about this during the IPFS call as well. Well, let's say you have one file, you've uploaded it to the IPFS network. Now the node that's uploaded it, some people have retrieved it, so it's that particular content is now available on the network in many different places. Now the moment you want to say update that content, right, you are not going to actually delete that content, right? You can make it invisible sort of, but you're never going to delete it. It's always going to be there. You'll only push a new version out of that piece of content. And then you'll have to update your links and stuff, which is your content IDs. But that's a very key point. Immutability is like built into the system in IPFS, right? That's very cool when you actually need it. When you don't need it, you end up wondering why. But you always know, I mean, when you don't need it, you just don't use it. That's the point. But it's always immutable in the sense that it'll be there. You could potentially go ahead and say this is stale. You could issue a request or a query, or you could issue a request to say that do not serve this content. Maybe some method might be available, but it's still there, because that's the whole point about distributed file systems. Once it's out, it's out. You don't know how many people have it at what point, etc., etc., etc. Right? But good point. That makes sense. So in the interest of time, I think the last piece that I will cover is, just let's look at some of these types. We talked about, let's say, something like peer ID, which is, I think that's very simple. We talked about transport a little bit. Then we talked about swarm. Now, swarm being the primary or one of the core types in this library, let's take a look at it and see what is it about. How is this actually built? So let's look at that. All right, so swarm is generic over something called T behavior. That's it. T behavior is nothing but something that implements network behavior. Network behavior is a trait, and this, I believe, is the most important, one of the core traits in libp2p. If you were to look at it, we'll see that it's a trait. It's got a static lifetime, which makes sense. It has an associated type, which we'll talk about what that associated type is. But basically, the associated type is a connection handler. And then there's actually two of them. One is an out event. So look at this. The documentation is pretty good, right? You don't have to guess what is happening because it's pretty good. Handler for all the protocols the network behavior supports. Okay, so for example, if we were designing, or rather if we just built our own ping application, the network behavior is ping behavior. then you'd want to know what the handler for that is. How, you want to say, okay, when you send a ping, what do I do? How do I handle it? So we are explicitly saying that, okay, every network behavior will have some sort of a connection handler to handle whatever, whatever data is being sent through. There must be some connection handler to handle that. All right. And then out event generated by the network behavior, and that the swarm will report back. Yeah. So as I mentioned, swarm is the one that's actually sort of tying the transport and the network behavior together. The swarm is like the manager. It is the one that is trying that's going to somehow connect these two other types. That means events from one type. That means the transport. When you get events at the transport layer, they sort of push to the network, the network behavior type. And then events from the network behavior are sent over to the transport, right? Yeah, I think that makes sense. Yeah, unless some new information that we get. But anyway, this is a trait. And this particular trait is talking mostly about what is my behavior as a node. That means what sort of behavior do I have? Do I have ping? Do I have some other query behavior, etc.? That is what this particular trait is. You can create your new connection handler. You can list the addresses of peers, because while in your network behavior, you can actually talk about addresses that this behavior is aware of. So if we just read this properly, we say that addresses that this behavior is aware of for this specific peer, and that may allow reaching the peer. Addresses that this behavior is aware of for this specific peer, and that may allow reaching the peer. The addresses will be tried in the order returned by this function, which means that they should be ordered by decreasing likelihood of reachability. In other words, the first address should be the most likely to be reachable. I don't think I understood that completely, but my guess over here is that the peer probably has multiple addresses. The addresses itself are, because multi-addresses actually do capture, the behavior. Because in the multi-address, you saw that, we include IP address, TCP port number, then the application level P2p, and then what type of P2p application. Yeah, right? That is an address. So this is basically returning addresses of the peer. That means the peer that's instantiated itself, it's returning the addresses saying these are my addresses. And then informs the behavior about an event from the swarm on connection. Basically, it's very simple. It's very straightforward. The other thing is this thing is also a future, right? Because obviously it's got the poll method. So it's the future. So network behavior, and I presume transport is also a future. So these futures will be passed to the executor and they will be polled using the poll method. Yeah. That sort of makes sense, right? Yeah. Okay, I think I should just find a abbreviation for questions and say Q. All right. Okay. I guess there are no questions, but since we're a little over time and I was only planning an hour, now we're almost 15 minutes over. I think we'll just sort of end it here. But before we go, just let me know your thoughts or your, ideas. I think Lavinia's suggestion of an IPFS particular focused talk to sort of see how libp2p and all the other dependencies are used to build out, let's say, an IPFS application would be a good idea. So any other thoughts from anyone else? Tweety. Okay. All right. So I guess that's a good note or a good point to end this particular stream. But I guess we'll sort of, extend this in another stream or during one of our sessions as well, where we'll talk about how this libp2p library or crate is actually used by something like IPFS and all the other extra pieces in IPFS like content addressing, Merkle DAGs, distributed hash tables with Kademlia, etc. We'll sort of take a look at that as well. But yeah, I think before we touch any code in the second case, we'd probably need to spend some time talking about the basics, or rather the concepts in IPFS. We'll do that so that we get a good idea, and then we can move to the code piece. Thanks. Thank you. Finally, it worked. Finally. Finally. I feel like I didn't spend a lot of money. I feel like my money, the speaker is still a good investment. Sorry, the mic is still a good investment. Thank you. All right, guys, so that's a wrap. Thank you so much. And we'll catch up in another Friday session. Okay? Ciao.